Equilibrium is the concept of balance between products and reactants. However, which side is more favored, one or the other, is dependent on the equilibrium constant. This equilibrium constant is specific for each different reaction and is temperature dependent. This experiment focuses on developing and calculating the equilibrium constant for the reaction or the balance equilibrium of cobalt tetrachloride and the cobalt hexaaquo complex. The balance between the cobalt ion bound to 4 chloride ions to form the cobalt tetrachloride complex, or bound to 6 water molecules to form the cobalt hexaaquo complex. It's the balance between these two that allows you to see the differences between them. And later on, you can see that it's temperature dependent, and you can figure out with the concept of heat and thermodynamics whether energy and heat is either a product or a reactant.
This experiment focuses on looking at the concept of equilibrium, and specifically the equilibrium of cobalt chloride. So previously, looking at the Le Chatelier's principle experiment, that was a qualitative experiment. You were looking at which direction the equilibrium is going to, either products or reactants. This experiment is a quantitative experiment. You're looking at how much of the reaction is going towards the products versus the reactants. What is that ratio? In the end, when a reaction is in equilibrium, that means it's not really happening anymore. The products and the reactants are balanced at a balanced state. But what is that ratio? How much product is there and how much reactant is there under those equilibrium conditions? And the equilibrium constant is the specific ratio that determines how much of each of the components is present in the reaction. So the chemical equilibrium constant really is a ratio of products over reactants, but it's also based on the stoichiometry of the balanced chemical equation. So equilibrium is based on concentration. If something is more concentrated or less concentrated, that will have an impact on the reaction itself and which direction that it will shift. So when calculating the equilibrium constant, this specific ratio, you're looking at the concentration of each of the individual components raised to the power of its stoichiometric coefficient. So it's still products over reactants, but you're taking into account the different ratios that they react with in the balanced chemical equation, as well as their concentrations to begin with. There are a lot of different types of equilibrium. The basic formula is the same. It's still products over reactants, and usually any equilibrium constant can be written as K E cubed, just meaning the equilibrium constant of the equation. But that's really for anything. There are a number of different ways to write that K with a different subscript, and that different subscript just means the type of reaction it is. So Kw is a very specific constant. That is the equilibrium of water itself. So water is in constant equilibrium with H plus ions and hydroxide, and this unique equilibrium is so important, especially in acid-base chemistry, that it has its own subscript. So Kw is the constant of the equilibrium of water. Ka and Kb are based on dissolving acids or bases. A Ka value is the equilibrium constant of an acid dissociating into H plus and its counterion. A Kb is the equilibrium constant of a base breaking apart into its individual components. There are two others. Formation constant, which is what this experiment looks at. It's the equilibrium between of the formation of a complex ion, which I'll go over a little later. And then for solubility, Ksp. This is referred to as the solubility product because it's the equilibrium of the solid salt dissolving. So the solubility that you've looked at before, looking at solubility data, this is related to the equilibrium of that solid salt and how much it's able to break apart before you can no longer dissolve anymore. And it's called the solubility product because when you're looking at a K value, when you're calculating these equilibrium constants, you'll notice that it's based on a concentration. So that means if it is a pure solid, there is not really a concentration associated with the solid, so its value would just be 1. There is no concentration. In Kw right here, water is liquid and a pure form. It's just itself. It doesn't have a concentration specifically. So, or at least in terms of the reaction and the equilibrium, so that is a value of 1. The same would be true for any solids. The concentration of the solid in the equilibrium constant would just be listed as 1 because you can't have a specific concentration of a solid. And because of this, the Ksp is just the product of the concentration of the individual ions. One way to look at equilibrium and going through these equilibrium calculations are ICE tables. And ICE refers to initial, change, and equilibrium. And I will go over this a little bit later, but just to kind of introduce you, the initial concentration is what would be present if the reaction never actually occurred. If time was paused, you mix everything together, and before the reaction takes place, what would be the concentration of each of the components in that test tube or in that beaker? That's the initial concentration. However, you can't pause time, and the reaction itself, because of any changes and because of Le Chatelier's principle, will change the concentration in one direction or another. It will either add concentration or remove concentration from the products and reactants. And the stoichiometry plays a role in that. Depending on what the balanced chemical equation is, that will dictate how much of a change occurs. And finally, equilibrium. So this is the concentrations that you're actually measuring. If you go in a flask, a beaker, test tube, and you're measuring a concentration or you're measuring something, that is in equilibrium. The reaction has kind of finished and it's in that balance state, it's equilibrium state. So to figure out how much the starting concentrations are or how much the change is, you're using this measured equilibrium concentration and you're overall finding these different components. As mentioned, this experiment focuses on the equilibrium of cobalt chloride, and it's two different complex ions. So you're going to be watching this video and looking at the differences in this chemical equation here. So looking at the two different complexes, there is the cobalt ion bound to 6 water molecules, and that will give a red color. There is also the cobalt ion bound to 4 chloride ions, and that will give a blue color. This is where the intense color cobalt blue comes from. This is only present though, or only visible in the absence of water. Water itself is part of this equilibrium reaction. And when water itself is part of the reaction, it can be looked at in a couple of different ways. You're seeing how water reacts and the equilibrium between the red component and the blue component. And this is where solvent selection can be very, very important. So solids can dissolve not only in water, but in other solvents as well. And in this case, in this example, the cobalt chloride is being dissolved in ethanol. And when it's dissolved in ethanol, you get the dark blue, cobalt blue color because there is no water or very little water present to drive the reaction towards the red color. But if you dissolve it in pure water, it's going to start out as that red color. There's an abundance of water. And when you're looking at something and choosing a solvent, especially when that solvent can be part of the reaction, it drastically changes the equilibrium of the reaction. And it's based on these kind of conditions. So here's an example of copper binding with ammonia. And water is part of this reaction. When you have the reaction in water, water is the pure substance, it's the solvent, it's everywhere. There's so much of it that the concentration is irrelevant. So because it's the pure substance, you have the product concentration of the copper tetraamine divided by the concentration of the copper water complex times the ammonia concentration raised to the 4th power because there's a 4 in the balanced chemical equation. However, if the reaction was done in an anhydrous solvent or a solvent that does not have any water in it, there is still water present in the reaction itself, but now the amount that is being utilized in the reaction is small enough compared to the rest where you can actually pay attention to it. So if the solvent is not water, Now the water can be included. And this is where solvent selection really plays a role, because if you were using a solvent that's in the reaction in one way or the other, it's really going to change the equilibrium conditions and those equilibrium ratios.
In this reaction, the solvent plays a key role. Because the reaction greatly involves the molecules of water, using pure water as the solvent will influence the reaction. Cobalt chloride hexahydrate solid is a red solid. However, depending on what the solvent is, the color of the solution can vary. Solutions dissolved in water retain the red color. However, if water is not involved and a solvent chosen is not water-based, such as anhydrous ethanol, the solution is a blue color. This blue color is where the term or coloring of cobalt blue comes from. Cobalt chloride in its pure state without water is a blue color, and it's only the presence of water that causes the red color to appear. To start the experiment, you will be preparing a solution of cobalt chloride hexahydrate using ethanol as the solvent. When the solvent of ethanol is used, these types of solutions are also referred to as tinctures. You will weigh out approximately 1 gram of solid cobalt chloride hexahydrate and add this directly to a volumetric flask. When the cobalt chloride is added to the flask, you can then add ethanol to the flask. You will fill the flask up to the 100 milliliter mark with ethanol. As you're filling the bulk of the volumetric flask, you'll want to end at the appropriate mark, and you should use a pipette to add the ethanol slowly until the 100 milliliter mark is reached. When the volumetric flask is filled with ethanol, you can stopper the flask and invert the volumetric flask several times in order for the cobalt chloride to dissolve. Afterwards, you will have a 100 milliliter solution of cobalt chloride hexahydrate in ethanol, and you will use this solution throughout the rest of the experiment.
So in this experiment, you're going to be preparing the solution in an anhydrous condition. You're preparing a solution of cobalt chloride in ethanol. And when you do this, you'll need to know what all of the initial concentrations are. And these concentrations, both of the chloride ion, the cobalt ion, and the amount of water in that flask are based on the mass of cobalt chloride hexahydrate that you're measuring and weighing out on the balance. So once you have the mass of cobalt chloride hexahydrate that's being dissolved in the flask, you could convert that to moles of cobalt chloride hexahydrate using the molecular weight. And for the concentration, you can divide that, divide the number of moles by the total volume. And the flask you're using is a 100 milliliter volumetric flask. So the total volume of solution is 0.1 liters. Once you have the moles of and molarity of the cobalt chloride, you can also see the moles and molarity of the individual ions themselves, both the cobalt ion, the chloride ion, and the water molecule based on the stoichiometric ratio within cobalt chloride hexahydrate. In every one molecule, there is 1 cobalt, 2 chlorides, and 6 water molecules. So when determining the number of moles, after you divide by the molecular weight, you'll multiply by 1 to get cobalt, multiply by 2 to get chloride, and multiply by 6 to get the moles of water, or the molarity of water. These are the concentrations in the flask itself. And in the experiment, you're mixing that with an amount of water. So you're taking 25 milliliters of that prepared solution and combining that with 25 milliliters of a 2 molar water solution in ethanol. And the final volume of that will be 50 milliliters total. For both the cobalt and the chloride concentrations, once you have mixed these together, mixed some of your sample and some of the water solution, you can determine the resulting concentration of both chloride and cobalt using the dilution calculation. So M1V1 equals M2V2. The initial concentration, that M1, is determined by step number 2 right here, where you're determining how much concentration, or what the concentration is in your flask. V1 would be 25 milliliters. You're using 25 milliliters of that solution. You're trying to figure out what the final concentration is, M2. And the final volume is 50 milliliters. You have 25 plus 25, so that gives a final volume of 50 milliliters. And from that, you can determine that initial concentration in your solution, in your mixture of both the cobalt ion and the chloride ion. Determining the concentration of water in your mixed sample is a 2-step process. You first have to account for this water that's coming along in with the solid. So you're taking some of this solid, which is cobalt chloride hexahydrate, that has water already associated with it. There's already water in that solid. And you have 25 milliliters of this initial concentration in your flask. So when you multiply those together, you can determine how many moles of water are coming directly from that solid. You can then use the M1V1 calculation to determine, or I'm sorry, you can use the moles per liter calculation again with the 2 molar ethanol. You're adding 25 milliliters of 2 molar ethanol. You know the volume and you know the concentration. So from that, you can calculate the moles of water that are being added to your solution itself. When you add those two up, you have the moles of water that are coming directly from the solid. You have the moles of water that are being added to that mixture, and divide it by the final volume of 50 milliliters, and that will give you the initial molarity of water. So when you mix these things together, you're starting out with cobalt, chloride, and water, and you have these initial concentrations. In the experiment, you're trying to figure out what all of these concentrations are at the end in a state of equilibrium. Once the reaction shifts and the equilibrium between the two complexes establishes itself, that's what you're going to be using and calculating throughout the report. But in order to determine those, you first need to know what you're working with. What is that starting amount? And this is how you would go about determining those initial concentrations of chloride and of water.
The experiment itself involves the preparation of a cobalt chloride solution in ethanol. That is an anhydrous solution. The only water present is that which is brought over from the solid compound. Cobalt chloride hexahydrate has 6 molecules of water for every 1 molecule of the cobalt chloride hexahydrate. By starting with the blue solution of the cobalt tetrachloride complex and adding a very small but known amount of water, the color of the overall solution is a blend. The solution color is a mixture of the blue cobalt tetrachloride and the red cobalt hexaquo color. The result is more of a purple solution. It's this purple solution that would have the color characteristics of both the pure blue cobalt tetrachloride complex and the red cobalt hexaquo complex. If you were to take an absorbance spectrum of either of the pure compounds, you would only see one peak, one primary wavelength of color that absorbs the most. However, using the blend of cobalt tetrachloride and cobalt hexaquo, there are 2 peaks. There are 2 competing molecules and complexes in equilibrium with each other. When these are combined, you get the color scheme of both of them. Using a spectrophotometer, you could obtain the absorbance of each of these different wavelengths and correlate that to a specific concentration of both of the complexes. Once the cobalt chloride solid is dissolved in the ethanol, you will be combining this solution with a known amount of water. You will be preparing 50 milliliters of a combined solution in a 50-50 split. You will measure out 25 milliliters of cobalt chloride tincture in ethanol and 25 milliliters of a 2 molar water solution in ethanol. In this experiment, ethanol is the solvent and water is one of the reactants and is involved in the equilibrium. You can measure out using your graduated cylinder 25 milliliters of your cobalt chloride solution and add that to a flask or beaker. You can then combine 25 milliliters of the 2 molar water tincture in ethanol. You will notice now that this solution is more of a purple color. This is a combination of the equilibrium products. The blue cobalt tetrachloride complex, which is found in ethanol, and the red cobalt hexaaquo complex, which is found in water. This purple solution is a combination of both of those two different complexes existing in equilibrium. When you have the solution prepared, you will then be placing some of that solution into 3 different test tubes. You're going to investigate how this equilibrium reaction works between these two complexes and how that relates to the temperature of the reaction. With the cobalt solution prepared and properly mixed to achieve a blend of both complexes in equilibrium, you can move on to the last part of the experiment, which is the temperature dependence of the reaction. The blend is a purple color, a mixture of the blue tetrachloride complex and the red hexaaquo complex. The reaction itself is temperature dependent. By placing the purple blend in an ice mixture for a few minutes or so, the equilibrium shifts to one side. This can be seen because after a few minutes or a couple of seconds, you can see that it's noticeably much more red than it was initially, especially towards the bottom of this test tube. As it's cooling down, the equilibrium shifts and favors the red hexaaquo complex. However, if you take this same solution and place it in warm water, the reaction itself shifts to the opposite end of the equilibrium, overall forcing it to go more to the tetrachloride complex and become a blue color. This equilibrium shift can go back and forth depending on the temperature. And overall in this experiment, you're looking at the temperature dependence of this equilibrium reaction by looking at the equilibrium constant at 3 different temperatures and plotting this to figure out the enthalpy and entropy of this reaction. With the 3 test tubes of cobalt chloride solution prepared, you will be placing one in ice and allowing that to decrease in temperature. And you'll notice the change in color as the temperature was decreased. You will also be placing one of these test tubes in a warm water bath. And you again can more predominantly see how the color changes as the temperature was increased. You will then be obtaining the absorbance using a spectrophotometer of all 3 of these solutions of cobalt chloride. at these 3 different temperatures. You will be obtaining the absorbance at 2 different wavelengths. One wavelength looks at the absorbance specifically of the cobalt tetrachloride complex. The other wavelength looks specifically at the absorbance of the cobalt hexaaqua or water complex. Using the absorbance, you can then convert these to concentration at equilibrium of both of these complexes in each of these 3 different temperatures. To obtain the absorbance of the 3 solutions at 2 different wavelengths, you will be using the spectrophotometer. Remember, these solutions were prepared in ethanol, so when calibrating the instrument, instead of using water, you should be using ethanol in the reference set. To begin, you will be turning on the instrument. Remember, this needs to be calibrated for each wavelength. You can first dial the wavelength to 515 nanometers. Adjust using the left-hand knob to a percent transmittance of 0. And then, placing ethanol in the sample chamber, you can adjust the percent transmittance to 100% using the right-hand knob. Now, this spectrophotometer is calibrated at 515 nanometers. With the instrument calibrated at 515 nanometers, you can now obtain the percent transmittance of each of your 3 samples, both at the raised temperature, room temperature, and at ice temperature. Throughout the experiment, you will be measuring using a thermometer what the 3 temperatures actually are. What is the room temperature? What is the temperature of your ice? And what is the temperature of your warm water? You will obtain the percent transmittance of each of these 3 solutions at 515 nanometers. Once this is done, you will then change the wavelength to 655 nanometers. Recalibrate the solution, or the recalibrate the spectrophotometer using ethanol, and then obtain the absorbance or percent transmittance of these 3 solutions once you have the wavelength adjusted and the spectrophotometer calibrated.
So once you have those initial concentrations, the initial concentration of chloride, the initial concentration of water, you need to figure out what that equilibrium concentration is. And you're going to do that by first measuring the equilibrium concentration of those 2 complexes. You're working with the balanced equilibrium between the blue cobalt tetrachloride and the red cobalt hexaaqua complex. Being that these 2 complexes, these 2 compounds have a color associated with them, you're going to be relating that the intensity of that color to their concentrations. And you're going to be doing that through the use of a spectrophotometer and using Beer's law, where the absorbance of a compound is equal to a molar absorptivity constant times a constant path length times the concentration of the compound. So you've already seen in previous experiments that this relationship is a linear straight line. And so long as the wavelength is not changing, the path length is not changing, the slope of that relationship between absorbance and concentration is equal to this molar absorptivity constant times the path length. In lab, you're using these different compounds, you're measuring that at different wavelengths, all keeping the same path length. So what we have already pre-calculated for you is the Beer's law relationship between absorbance and concentration at a couple of different instances. So in lab, you're going to be first measuring the absorbance of each one of your solutions at 655 nanometers. And what that absorbance relates to is the direct concentration of this blue cobalt tetrachloride complex. And the relationship is that the absorbance equals 139.09 times that concentration. So when you measure the percent transmittance at 655, you'll be converting that to an absorbance, and then using that absorbance and this equation, we'll calculate for each of your samples, what is the equilibrium concentration of cobalt chloride tetrahydrate. Next, you will use that concentration to calculate what the absorbance would be at a different wavelength. So once you've already established what the concentration of cobalt tetrachloride actually is, you can change the wavelength, and that concentration's not changing, but the wavelength is. This absorptivity constant is changing, and so that changes the slope of the line only, but the concentration is still the same. And when you do this, when you take that concentration and plug it into this relationship here, where the absorbance equals 18.321 times the concentration of cobalt tetrachloride, that gives you the absorbance at 515 nanometers. And the reason for this is because in that second wavelength, the 515 nanometers, that contains signal or some absorbance from both of the compounds. So that's contains absorbance from both the cobalt tetrachloride complex and the cobalt hexaaqua complex. So once you have the absorbance of the cobalt tetrachloride at 515, you're going to be subtracting that from your measured absorbance. Again, this measured absorbance at 515 is a combination of both absorbances from both of the different compounds. There's signal overlap. They're stacked on top of each other. So you'll then subtract your measured value from this calculated value to obtain the absorbance of just this cobalt water complex. And last, once you have the absorbance of that cobalt water complex, you can put that into one final Beer's law relationship where the absorbance is equal to 5.4905 times the concentration of the cobalt water complex. So you have this absorbance, you can plug that in here, and you're finally solving for the concentration, the equilibrium concentration of the cobalt water complex. So from these measurements, you're able to determine the equilibrium concentration of the cobalt chloride complex, that's the blue color, and the cobalt water complex, which is the red color. The initial concentrations of these are 0. So looking at in the ice table before the reaction starts, the concentrations are 0. And what you're measuring is the equilibrium concentrations. And you can then use these equilibrium concentrations and the stoichiometric ratios of cobalt and water for every 1 cobalt water complex. This uses up 6 water molecules. And for every 1 cobalt chloride complex, it uses 4 4 chloride ions. So with those equilibrium concentrations and the initial concentrations that you're starting with of the chloride ion and the water molecule, you can determine by subtraction what is the equilibrium concentration of the chloride and the water. So you're measuring the equilibrium concentrations of the cobalt chloride and the cobalt water complexes, and then calculating the equilibrium concentrations of the chloride ion, the free chloride ion, and the free water molecule. So with knowing how much initial chloride and initial water you have, you mix that together with a little bit of additional water, and it went from that dark blue color to more of a purple color. There's an equilibrium occurring. There is both the cobalt chloride, or like the cobalt tetrachloride present, and the cobalt hexaaquo complex. So both the blue and the red is present at the same time. Based on the absorbance readings from the blue sample, the cobalt tetrachloride, and the cobalt hexaaquo sample, the red component, using the absorbance values, you can figure out the concentrations at equilibrium of the 2 complexes. But to solve for the equilibrium constant, you need to also know the concentrations of the other components, the free-floating chloride and the free-floating water that's still present in the vial. So you know from the initial concentration, the total amount of chloride and the total amount of water. This is the initial concentration. It can't be any more than that. Some of it is being bound to the cobalt, some of the chloride and some of the water. It's both being bound to that cobalt and taken away. So it's no longer free floating around. There's some of it being bound to the cobalt. So if you subtract these two, then you end up with the total free floating concentration of chloride and free floating concentration of water. So for every 1 molecule of cobalt tetrachloride, there are 4 chloride ions that were used to create that molecule. For every 1 molecule of cobalt hexaaquo complex, there are 6 water molecules. So you have to account for that using those stoichiometric ratios. And another way to set this up and to see these, or to calculate these equilibrium concentrations, is through the use of an ice table. So before the reaction even begins, if time was frozen when everything was mixed together, the concentration of the 2 complexes would be 0, and the change is adding to that 0 to obtain the equilibrium concentration. And these are determined directly from the absorbance values from the spectrophotometer in lab. The chloride and the water concentrations initially are based on the sample mass and the total volume that's used in preparing those initial solutions. So you have the initial concentration of chloride, and the initial concentration of water is, again, based on the sample mass and the amount of excess water that was added to change the color to that purple color. So you have these starting concentrations. For each cobalt chloride that is present at equilibrium, it is using 4 chloride ions. So if you know how much there is to start, and you know that for every one of these, it uses 4 chlorides, that means 4 times the concentration of cobalt chloride is the concentration that is bound to cobalt. So you take the initial concentration minus 4 times the concentration of cobalt chloride. That will give you the equilibrium chloride concentration. The same is true when calculating the free water molecules, except this time it's based on the equilibrium concentration of the cobalt hexaaquo complex. For every one of these cobalt hexaaquo complexes, there are 6 water molecules associated with that. So if you know the starting initial concentration of water and subtract 6 times the equilibrium concentration of the cobalt hexaaquo complex, you obtain the equilibrium concentration of water, the free-floating water that is still throughout that test tube, still throughout that solution. And when you do this, you have the full balanced chemical equation, and you have the reactants, you have the products, where you have the free equilibrium concentration of cobalt tetrachloride complex, the equilibrium chloride ion, equilibrium cobalt hexaaquo complex, and the equilibrium water concentration. So when you're using these values, you're using the concentration of the cobalt hexaaquo complex, the concentration of free-floating chloride, the concentration of cobalt tetrachloride complex, and the concentration of free-floating water. These are all at equilibrium, and it's temperature dependent. You can see that when you increase the temperature, it becomes more blue. It becomes more of that bright cobalt blue, so it's making more of the cobalt tetrachloride. When you decrease the temperature, it becomes more red. It's making more of that cobalt hexaaquo complex. So the equilibrium is temperature dependent, and you can look at that and measure from the equilibrium by each of these 3 different temperatures. You look at the equilibrium constant, and from that you can determine the thermodynamic properties of this equilibrium equation. So you can see how the temperature or the energy of the environment can affect the equilibrium. You can see that in the changing of the color, going from the equilibrium purple, where they're nice and balanced together, the 2 different complexes, and you increase the temperature, it goes more blue. You decrease the temperature, it goes more red. The temperature plays a critical role in the equilibrium. And because of that, you can relate the two large concepts in Chem 2 relating equilibrium and thermodynamics based on the energies. And what you're doing is you're going to be plotting a Van Hoft plot of cobalt chloride using your data. So for each of the three temperatures, you're calculating what is the equilibrium constant. And then when you plot the natural log of the equilibrium constant on the y-axis versus the inverse temperature on the x-axis, this is what's called the Van Hoft plot. And it should be a very straight linear line. And from that, you can determine the equation of that straight line. You can just solve for a slope and an intercept value. Now, these are, it is important when you're making the Van Hoft plot, the temperature does need to be in Kelvin. So it's 1 over the temperature in Kelvin. And the equilibrium constant, you're looking at the natural log. So this is ln of the equilibrium constant. And you're going through and plotting this to solve for both the slope and the intercept value in this straight line. So the slope and intercept of that value or of that line are related directly to the thermodynamics of that equilibrium equation. So the slope is related to the enthalpy value. The slope is equal to negative delta H over R, so the gas constant, and the intercept is related to the entropy, so delta S over R. And from these equations, from that slope and from that intercept, you can calculate the enthalpy, you can calculate the entropy, and you can, using that and the different temperatures, you can solve for delta G and get the Gibbs free energy for these different equations, and also figure out at what temperature does this reaction become spontaneous? At which temperature will it actually go from red to blue or blue to red? What is that final temperature?
This experiment combines a number of different concepts that you've gone over in Chemistry 2. It's taking an equilibrium reaction, which is prepared using different moles and different ratios, and you're determining the equilibrium of this at different temperatures. You're looking at the ratio of product and reactant at these different temperatures, and from the change in the equilibrium constant, you can then calculate the enthalpy and entropy, and overall you can see at what temperature would this reaction become spontaneous. It's relating the two very important concepts of equilibrium and thermodynamics to show that many times in all of these reactions there is an equilibrium, but there is also the thermodynamic data and the thermodynamic properties of these different reactions that are always there in the background. It's relating these two concepts, and as you go through this and look at all of the different observations and calculate those different equilibrium constants and thermodynamic properties, you'll get a better sense of how these types of very different chemistry concepts can be related in chemical reactions.